Good evening, everybody. We're supposed to find all ordered pairs of integers that satisfy this equation. This is a problem that I found when I was working on a more difficult problem that I haven't solved yet, and I'll let you know when I solve that problem and how knowing this will help me solve the other problem. But this is a slightly easier result that I just recently proved that I can use to solve the other problem, but there's a bit more to it. But anyway, we're looking for all ordered pair integers k comma n. And you know, z stands for the integers, the positive and negative, including zero integers. Find all of these that satisfy this condition. 16n is equal to k squared minus 120. Now, you can check quickly to see that neither k nor n can be equal to 0. So I'll go ahead and note that right now, although it's not important. The solution process would figure this out whether I mention this or not. But notice that if n is equal to 0, that would intimate that 120 is a square integer, which it's not. It's close. 11 squared is 121, but 120 is not a square integer. Also, if k was equal to 0, that would intimate that 16 divides 120, and it doesn't, because 120 only has a factor of 8. 8 times 15 is 120. So neither one of these are solutions, just a quick inspection. All right. Now, another way to rewrite this equation that makes it slightly easier to work with is just to bring the 120 to the other side and factor an 8 out related to what I just said earlier. And so we get k squared if and only if 8 times the product, or 8 times the quantity 2n plus 15 is equal to k squared. We just simply factored an 8 out of from the left-hand side. Okay. Now this is a pretty well-known result. You're asked to prove this in some number theory courses. Sometimes it's presented as a result within the section of a number theory course. Other times it's presented as a homework problem. But anyway, this should be very clear. An integer is a perfect square if and only if, that's short for if and only if, it's just a wordy way to say equivalent. Each exponent in the prime factorization is even. And if you think about taking the square root, you have to half all of the exponents, right? Well, if you have an odd exponent, it's not going to half. It's going to end up being an irrational number. So this is a very useful fact right here. An integer is a perfect square if and only if. That is, a perfect square means it's just equal to another integer squared. Perfect, sort of superfluous in my opinion. Okay, so if we take k comma n to be a solution, observe that k squared must be a multiple of 2 to the 4th. Now we can call that 16 if you want. It's not, but it's better to call it 2 to the 4th, because you can actually, when you take the square root of 2 to the 4th, you get 2 squared, right? But 8 is 2 cubed, right? That's the odd exponent. We need an even exponent. We need an even exponent, but right here we have 2 cubed and an odd exponent. So if there's going to be a solution, that implies that you don't see any 2's over here except for 2n plus 15, and 2n plus 15 is an odd number, right? But in order for k squared to be a multiple of 16, which is forced, we would have to have 2n plus 15 is even. Right, folks? And I hope that makes sense. It's fairly clear. This is one time where I don't think modular arithmetic is that great. I think it's better just do it directly like Rex Schneider recommends. Okay, but we have 2n plus 15 right here. We need 16 to be a factor of this entire object here. We see an 8 right here, so there has to be at least 2n plus 15. There's no choice but for it to be even. But this is clearly false, right? Because you could rewrite this as 2 times n plus 7 plus 1, right? Most people don't need to see this written down, but just for the sake of being complete, and the fact this is a short problem really. See, so that's odd, right? Okay, so this is obvious, even though the logic from here indicates that 2n plus 15 is even, it manifestly is odd, right? So that came from assuming that kn is a solution, and kn being, maybe I should be more cautious here, kn a member of z cross z, right? The Cartesian product of the integers. So this is, I guess we contradicted. It's a contradiction. which arose from the fact that we assumed we had an integer solution. Okay. Okay, so we made the assumption that we did have an integer ordered pair solution. Right here, if Kn is a solution, yada yada, we get to this contradiction right here. So that means there are no, okay, we come to the conclusion that there are none. Okay, there are no ordered pair solutions. I'll come up here. I wish I could keep everything together, but I don't. Never mastered that. Okay, so there are no, there are none. Find all. No solutions. Okay. It's funny how you discover these things. This isn't a hard problem by any stretch of the imagination, you know, but it does require some thought because you do this factorization and then you take it. The big result here is that an integer is a perfect square if and only if each exponent in the prime factorization of said square is even. Okay. So again, very simple logic right here, I think. So so again, no solutions to this, what do they call it, a diophantine equation? Okay, thanks for viewing.